Now in logic, we have negation. It would be nice to have negation in logic programming as well. Let's see how one can do that. Here's an example. It's the graph example yet again. Suppose we want to express that two vertices in a graph are not connected by a path. We've got the first two clauses in the definition of the path predicate, but then we add a clause defining the unconnected predicate. X and Y are unconnected if X and Y are vertices, and it's not the case that there is a path from X to Y. It would be nice if we could simply write not, and indeed we can, but then we must think about how we can interpret negation. When is something not the case? And what we do in Datalog and in Prolog is that we take the negation as failure interpretation. And I will explain that now. It's central that the only formulas we can negate are atoms. We cannot negate rules. We can only negate atoms. And we introduced new formation rules to do just that. Now we distinguish between positive and negative atoms. So an atom can be a positive atom and it can be a negative, a negated atom. And those negative atoms cannot appear in the head of the rule. They can only appear in the body. That's important. And also we have to do something about the semantics, because now we've extended the syntax. We have to extend the semantics as well. So now we have to deal with nots. When is not P of t the case under an interpretation? It's the case if P of t is not an atom in the interpretation. So saying that P of t does not hold is the same as saying that we could not conclude P of t according to our interpretation. But then we have to be very careful, because things can go awry if we don't pay attention. Here's a bizarre program. This one. Oops, it says that P of x is the case if Q of x is not the case. And Q of x is the case if P of x is not the case. This looks fishy. And indeed it is fishy. Suppose the Albrar universe contained one term, 17. Say, it's not important which one it is. But because we use negation as failure, we can actually get two models of a program. One that says that P of 17 is the case, and another that says that Q of 17 is the case. It's not hard to check that these are both models, but they are incomparable. This is not a subset of that, and that is not a subset of this. There is no unique minimal model. In fact, neither of these can be minimal. So there's something fishy going on. We should be required to disallow bizarre programs. What is it that we disallow? We disallow circularities. And the way to disallow circularities is by requiring the predicates of our program to be ordered in strata. Strata is Greek for layer. So each stratum gives rights to subprogram PI that contains the clauses defining the predicates in stratum I. That way we can order our program, or rather the clauses in our program. So here are the ones that talk about the predicates in stratum 1. Here are the clauses that talk about predicates in stratum 2, and so on. We can also talk about, in P2, we can talk about predicates in P1. But we can only talk about earlier predicates. We cannot talk about predicates that appear in later strata. Because what we need to require is that for every index I, the clauses in the predicates in stratum PI can only mention negative atoms from predicates that were defined in earlier strata. If there's no negation involved, there are no problems, but as soon as we've got negation, we have to be careful about the negated atoms. And that's why stratification is necessary. And the stratification of a Datalog program, that's a partition of the predicates such that if there is a rule B and something else implies A, then this rule will define A to be the case. And when we're defining A, B must already have been defined. So if the predicate A is in the stratum I, then the predicate B is in some earlier stratum with a smaller index. But it can be the same because it doesn't matter because there's no negation here. But if we have a rule in which we're defining A using B and B is negated, then the predicate that's being negated must be in an earlier, strictly earlier stratum than A. This is a natural requirement because in this way, whenever a predicate A depends on some other predicate, we know that the facts in that other predicate have already been computed. So we know what they are, and we can easily check if this condition is met. Not every data lock program can be stratified. The counterexample is the program we saw before, the silly or bizarre program. If we had a stratification, then that would require that P appeared in an earlier stratum than Q, but also that Q appeared in an earlier stratum than P, and of course we can't have that. So we must be able to check if programs can be stratified or not. But that's not all. We also need to require that the variables in a negated atom also appear in some positive atom in the same rule, because if that was not the case, we couldn't compute the values of the variables. For instance, here's a rule that's not so good. X and Y are unconnected if there is no path from X to Y. But if we write this, we know what X and Y are. They are vertices. They must be vertices. So we can find the values of X and Y before checking that path of X and Y doesn't hold. So there's safety about negation, that the atoms that we negate must be ones that we can compute. Now back to the example. What we saw before was this graph program. It's got 3 predicates, it's actually 4. It's got path, edge, vertex, and unconnected. 1, 2, 3, 4. And the way to stratify them, well, how do we stratify them? Unconnected is defined using a rule that mentions a negative atom, not path. So path must have been computed before we could find out if X and Y are unconnected. So path must live in an earlier stratum. Path also mentions edge. So path and edge and vertex should live in the same stratum, and P1 should live in a later stratum.